In this video, what I want to talk about is how we can use a technique called calorimetry to determine the specific heat capacity of a metal. So what we're doing is we're taking water, and my initial temperature of my water is 23.7 degrees Celsius. And we're going to take a piece of the metal. So my metal, which I've heated up to a temperature, an initial temperature equal to 100 degrees Celsius. Okay, and I'm going to drop that metal into the water. And when I do, they're going to reach thermal equilibrium. We'll have a final temperature for both of them. In this case, was 27.8 degrees Celsius. Now I want you to notice something. Notice that the metal changed temperature, had a bigger change in temperature than water. So because of that, since the change in temperature of the metal is greater than the change in temperature of water, and it's much greater, and yeah, we do have half as much, okay, but we get way more than double the change. We can predict that our heat capacity of water is less than the heat capacity of our metal is less than the heat capacity of water. Now, I'm not talking about quantitatively because we do have less metal, so we would expect its temperature change to be different. But if you just kind of look at a ballpark of this is a pretty significant difference. So it's good to be able to kind of compare some of that qualitative prediction in this case. Now, Q of my metal is going to be equal in magnitude, opposite in sign of Q of my water, right? My metal lost heat, my water gained heat. But it would be equal in magnitude, opposite in sign. So my first step will be to solve for Q for my water. So that's going to be my mass of water. If it's not specified, you always assume that the density of water is 1 gram per ml. So that means I have 100.00 grams of water. Problems will give you, I don't make my students memorize the specific heat of water, but there it is. I would give that to you kiddos if you're mine, just FYI. And then it's the final, remember always final minus initial. So Q for my water was 1.72 times 10 to the third joules. Okay, so that's step 1. Now, step 2 is to recognize that Q of my unknown metal is equal in magnitude but opposite in sign of my water. Heat transfers from hot, so heat transfers from hot into cold, right, until they reach thermal equilibrium. So whatever one loses, the other one gains, assuming a well-insulated system. And so that means I would have minus 1.72 times 10 to the third joules. Now the question is calculate the specific heat of the metal. So that's where step 3 comes into play. So step 3, I'm going to use MCAT. My Q, 1.72 times 10 to the third, heat, is equal to mass. My mass of my metal is 59.047 times the heat capacity of the metal that we don't know times the temperature change. Always final minus initial. If you don't do it that way, you're going to mess up your signs. Okay? Now, bear in mind, whoops, my mind started going ahead of me here, so minus 100. Bear in mind that a heat capacity is always a positive value because it's defined as the heat needed to raise, so heat needed is positive, to raise the temperature of 1 gram, 1 degree Celsius. So if we did this algebra right, so check your work, I got a heat capacity for my metal equal to 0.403. Indeed, it is much less than my water. Grams, degrees, Celsius. Now, what you could do then is go look up the heat capacity of metals and maybe identify your metal based on its heat capacity, because the heat capacities are very characteristic of metals, assuming you're looking at the same density of the metal. So you do have to be a little careful, but if you're given a list of metals, you can often identify your metals by comparing the heat capacities. So I know it sounded complicated, but it's about doing an MCAT, changing a sign, doing an MCAT. Hopefully you're wrapping your mind around that. If not, rewind the video. Thanks for watching. Take care.